All right, everybody. Unfortunately, I inadvertently deleted the file from the actual lecture itself. So what I'm going to do is just do a screencast from my office on the material that we covered on Friday, yesterday, the 4th of November. So today we're going to be talking about addition reactions, of course, and we've already talked about a number of things that we can add across a carbon-carbon double bond. And so today we're going to focus a little bit more on some of the mechanistic details of these addition reactions. So one of the things that we can do is, excuse me, is if we have an alkene and we have a halogen, and the halogen here has to either be bromine or chlorine because fluorine is explosive and iodine is reversible. So really the addition of chlorine or bromine across a carbon-carbon double bond is the only thing that's really practical here. And so when you do that addition, what you end up getting is what's known as a vicinal dihalide. You've added two halogens across the carbon-carbon double bond. And they're vicinal because they're on adjacent carbons. If the additions happened on the same carbon, we would call that geminal. So these are vicinal dihalides. And as you can see in the additions, these are quite clean reactions. So if you start off with an alkene, for example, like cyclohexene, bromine, you get the vicinal dihalide, 1,2-dibromo cyclohexane. Notice there's no stereochemistry shown here. However, we know that the stereochemistry has to be trans. And the reason that it has to be trans is because of the mechanism. So what happens in the first step of the addition, the pi bond from the alkene reacts with one of the halogens. And of course, halogen as halide is a pretty good leaving group. So we show the arrows like this. So the electrons come to the halogen, the halide leaves. But at the same time, one of the lone pairs of electrons on the halogen that's being attacked will also attack the other carbon that's becoming electron deficient. And in doing so, you get this bridged holonium ion. So if it's a bromine, we would call it a bromonium ion, for example. And so now we've got this strained three-membered ring, and we've got halide, which can function as a nucleophile. And so what happens now, in a kind of a similar fashion to an SN2 reaction, although this isn't an SN2 reaction, the halide comes in from the backside, breaks that weak carbon halogen bond, and this functions as a leaving group. And it just so happens that the leaving group stays attached to the molecule. And so in relieving that ring strain, that's the driving force here, and you end up with the trans dihalide. So it's this three-membered ring that explains why you have to have the halogens added in a anti-fashion, okay, or trans to one another. Now, we believe that this has to be the case mechanistically because we could also draw a mechanism where the pi bond simply reacts with the halogen and generates a carbocation. However, if we had a carbocation that was generated, we would expect a mixture of both syn and anti diastereomers of addition of the halogen, and we don't see that at all. I mean, this is very, very selective, or specific, I should say, for the anti-addition. And so we know that the carbocation wouldn't be stable because, in fact, the halogen could donate a pair of electrons to give us this strained three-membered ring, and given what is called here as a bridged holonium ion. Now, you might ask yourself, well, why would we want to do this? Because halogen, of course, is electronegative. It doesn't like to be positive. Three-membered rings are unstable. All those statements are true. However, everything here has an octet. And so even though they are unstable, they're more stable than a carbocation. And so everything's fine there. Oops. So this was some stuff that we actually covered in the inverted lecture. So if you take cis-2-butene and you add bromine across that carbon-carbon double bond, you actually end up with a pair of enantiomers. And so I strongly encourage you to actually do this exercise using your model kit. So if you take cis-2-butene, you get a pair of enantiomers. If you start off with trans-2-butene and you add bromine, you actually get a meso compound. And you'll see that if you do this addition with cis-2-butene, you only need to make one of the enantiomers. You don't have to make both. And then with trans-2-butene, just make one of the meso compounds that they have shown here. And what you'll see is that, in fact, these are not the same. So this is evidence that this is actually a very specific reaction. Okay, and so the stereochemistry of the alkene dictates what kind of stereochemistry you're going to get in your products. And so these are stereospecific reactions in the sense that one stereochemistry of your alkene will give you a particular stereochemistry in your products. If we run these reactions in the presence of water, we get halohydrons. So you get OH attached to one carbon, you get the X attached to another carbon. And again, you can do this quite easily. Alkene, water is your solvent, bubbling through chlorine gas or adding liquid bromine. And you can get these halohydrons quite easily. And these are actually very, very useful molecules for a variety of reasons, which we'll talk about in a moment. In the halohydron formation, you are going to go through that three-membered ring, that halonium ion, and that's going to dictate the stereochemistry that we need to talk about. So anytime you have an alkene and a halogen, X2, always make that three-membered ring, that bridged halonium ion. And so we have this three-membered ring formed. We have the halide as a leaving group. And now water comes in and attacks from the back side, breaks that weak sigma bond in the three-membered ring. You end up now adding OH and tied to the halogen. And of course, this is basically a protonated alcohol. Water comes in, deprotonates that, and you end up with the halohydron intermediate plus acid. So basically, if you take bromine, for example, Br2, and do this reaction, you're going to end up with a halohydron and a molecule of HBr, basically, because, of course, H3O plus and Br minus is HBr in water. So that's the way that reaction is going. Now, you should ask yourself at this point, why doesn't the halide simply come in and attack the carbon? A couple of reasons. One, we're running this reaction in water as our solvent, and we know that water is about 55.5 molar concentration, so it's there in much more quantity, if you will, than any amount of halide that you can get. Okay, so that's number one. So we know that nucleophiles in these SN2 type reactions like we have here are going to be dependent on the concentration of the electrophile and the nucleophile. So you got more water, that should be the nucleophile that functions as the nucleophile. Another reason is of course, the halide ion, the anion, is hydrogen bonded to water, and so it has this solvation shell around it that kind of protects it from functioning as a nucleophile. And so water then gets a boost from that as well, because it's actually on the outside of the halide. So even if the halide tried to approach the three-membered ring, there's still water around it, and the water will end up reacting. It turns out that the formation of bromohydrons can be conducted in the presence of what's known as NBS, N-bromosuccinimide. And what happens here is NBS slowly decomposes to form bromine. And we'll learn more about that mechanism in Chapter 10. But for now, let's just keep it simple. And anytime you see NBS and water, note that these things will just, this will just slowly decompose to give us bromine. And it turns out that this is a convenient way to deal with bromine. Bromine by itself is a pretty nasty liquid to deal with. There's always a lot of these brown fumes, vapors that are coming off of it. You can't breathe it. It's toxic. However, NBS is a white crystalline solid. Doesn't require a respirator or anything to weigh out on the balance. Just some safety gloves and normal safety precautions that you have to do all the time in the laboratory. And so it's a much more convenient reagent. So if you take NBS, water, alkene, you're going to get these bromohydrons. Now the DMSO, the dimethyl sulfoxide, is really there to solubilize both the alkene and the NBS. And so it's basically just a solvent to make sure that everything dissolves. It doesn't really play a significant role in the formation of the bromine from the NBS. Now, these halohydrons are also formed in an anti-fashion. So the only way that we can really tell that is if we take a constrained alkene, in this case cyclopentene, react it with bromine and water. And what you'd find, of course, is that the bromine and the OH are anti to one another. And in this case, we get a pair of enantiomers. These are two chiral centers. And so we have two enantiomers to deal with. If you build the models of these, you'll see that they are non-superimposable mirror images of one another. But what you notice here is that it doesn't matter which carbon gets the bromine and which carbon gets the oxygen from water, because there's a mirror plane of symmetry that runs through this molecule. However, that's not the case in the example down here. So if we look at this alkene, we can see that one carbon of the alkene has simply two hydrogens attached to it, while the other carbon of the alkene has two methyl groups. So you can imagine the bromine going to the least substituted carbon and the OH going to the more substituted, or vice versa, the OH going to the least substituted and the bromine going to the most substituted. And in fact, what happens is you basically follow Markovnikov's rule, and the OH is going to go to the most substituted carbon. And so this is the only product that's formed. And the reason is because in the reaction, you go through the bridged bromonium ion intermediate again, and the nucleophile is going to attack the most substituted carbon. And that might seem counterintuitive. After all, there's all this steric hindrance going on here, and so the nucleophile should be slowed down. It should be faster to attack this carbon of the three-membered ring. And that's a true statement, but it turns out that this bond between this carbon, the most substituted carbon, and this bromine is actually the weakest bond. And so the nucleophile is going to attack the carbon with the weakest bond to the leaving group. And so if you think about that, we've got bromine that's positively charged. And you know that bromine is electronegative. It doesn't like to be positively charged. So it's going to tug on these bonds, if you will, and try to pull more electrons to itself. And it turns out that it can pull the electrons from this bond a lot easier, because if we pull electrons from this bond and put them closer to bromine, that's going to put a partial positive on this carbon. And since this carbon is more highly substituted, we know that it can handle that partial positive charge by inductive effects a lot easier. And so the water actually ends up attacking the most substituted carbon, breaking that weakest bond, and you end up getting your bromohydrin products. Now, I mentioned that halohydrons are very, very important for a variety of reasons. And this is an actual preparation of estrone, which is a female sex hormone. And so if you look at this, you start off with this four-ring structure. We've got a single alkene that is reactive. If you take this and you simply bubble through chlorine in the presence of water, you get this chlorohydrin. And it follows the rules that we just said, in that the chlorine is going to go to the we're going to get the chlorine adding here and the OH on this particular carbon. And now you get this chlorohydrin, and you probably have to separate the other regioisomer that you would get. But nonetheless, you get this chlorohydrin as the main product. You take a base. The base will deprotonate the acidic hydrogen on an alcohol. Remember, alcohols are about a pKa of around 16, 17, 18, somewhere in that ballpark. Since this is a tertiary alcohol, it'll actually have a slightly higher pKa than that. But nonetheless, you deprotonate, and now you will have an alkoxide, which can function as a decent nucleophile. It can come in from the backside, kick out the chlorine, and you end up with this epoxide. And this epoxide, in one step, you can rearrange that epoxide, and you get estrone. The cool thing about this is that this is actually an industrially synthetically useful reaction to make a pharmacologically active compound. And again, notice everything here is sophomore level organic chemistry and general chemistry. All right, so this is chlorohydrin formation, acid-base chemistry, nucleophile attacking an electrophile. You get an epoxide, and then this chemistry would be the only chemistry that you're not familiar with. But a lot of general chemistry and general organic chemistry at the sophomore level used here to do these types of reactions. So I told you all to do this concepts test. I'm not going to go over that here. Basically, you're getting a bromohydrin in the top example, of course. In the bottom example, you're getting a chlorohydrin. So I suggest you stop this screencast at this moment. Work through those problems on your own. If you have any trouble with them, please come and see me. Now, let's talk a little bit more about organic synthesis. So let's suppose you come into the lab and you have cyclohexanol, but you really need 1,2-dibromocyclohexane. Of course, these would have to be trans to one another. There doesn't exist a single reaction that can do this transformation. So we need to start thinking about this. This is the product I want. This is the starting material I have. How can I make this happen? And so what we do is we start thinking about this backwards. So I know I can get 1,2-dibromocyclohexane if I have an alkene. So if I had cyclohexene, I could make this pretty easy. Just add bromine to it, right? But I don't have cyclohexene. But I know that I can make cyclohexene from cyclohexanol using either E1 or E2 elimination by dehydration, right? So if I think about that, I can simply take my cyclohexanol, treat it with sulfuric acid, for example, or phosphoric acid, whichever you like, and I could get cyclohexene out of that. Then simply take the cyclohexene, react it with bromine, and I can end up with the product shown here. This is one of the things that you really need to pay attention to, is how you do retrosynthetic analysis. So almost always when I give you a product and ask you, how could you make this? You need to think from the product and work your way back to starting materials. And again, this is very, very important for you, for those of you who want to go on and be physicians, because this is exactly how you have to think when you're treating your patients. A patient comes in with a disease, you have to figure out by thinking backwards what could have caused that. And so this is an excellent set of training for you in preparing for that type of thinking. Okay, so again, working backwards, we need cyclohexene, we need cyclohexene from cyclohexanol, so the forward synthesis would just be a two-step synthesis. We would take the cyclohexanol, sulfuric acid, we would make cyclohexene as a synthetic intermediate, which we would isolate, and then we would drip in bromine and we would get the dihalide that we need. And of course, these would have the anti-configuration around the bromines would be trans to one another. We can also add across a carbon-carbon double bond two OHs. So these are called glycols when you have an alcohol and another alcohol that are vicinal to one another. And so these are known as either 1,2-diols or glycols, or typically how we refer to these, and I almost always refer to them as glycols. Basically, if you look at this is the addition of hydrogen peroxide across a carbon-carbon double bond, H2O2, right? That's basically what we're adding across this carbon-carbon double bond. However, in the next slide, you'll see that we're really not using hydrogen peroxide to do this. So it's not really convenient. There are two possible ways that this can get added. You can imagine having the anti-stereochemistry, very similar to what we had in the halogen addition, or you can imagine the syn addition, where the two OHs are actually on the same side. It turns out that the reagents that we're going to talk about today will only give us the syn addition, and let's talk about that now. So, two ways to do this. I can take cyclohexene and I can get the cis-1,2 cyclohexane diol, or the glycol here. I can use potassium permanganate under basic conditions, so a little sodium hydroxide and water, and you can get the two OHs added to the same side. We'll talk a little bit about that here in just a moment. Important to note that's not actually listed here is this must be kept cold to do this reaction. So potassium permanganate, water, and hydroxide, if you do this at high temperature, these alcohols actually further react and decompose and do other things that we'll talk about in a later chapter. And so potassium permanganate has some issues. You have to really be careful with the temperature. However, you can use osmium tetroxide in a two-step process where you take the alkene, osmium tetroxide, and then you reduce off the osmium with sodium bisulfite in water, and you can get the glycol here as well. And notice the stereochemistry is exactly the same. This is a little more tolerant of temperature and other things like that, and so there are some advantages to using osmium tetroxide. The big disadvantage to osmium tetroxide is that it is highly toxic. It's a lot more toxic than potassium permanganate. In fact, just to give you kind of an idea, potassium permanganate is actually added to domestic drinking water storage ponds to kill bacteria in small quantities, not in huge quantities. We would never add osmium tetroxide to local drinking water pond reservoirs because it is highly toxic. There's another disadvantage to osmium tetroxide, and that is its cost, and we'll talk about that in just a moment. Now, if you look at these Lewis structures for potassium permanganate has this structure. So you can see there's the manganese metal, the two oxygens. You can see how the chemistry occurs. So the pi bond reacts at one of the oxygens. Those electrons go to the metal. The other pair of electrons from this metal oxygen bond go to the other carbon. And that's how you get the syn addition. If you actually build a model of this, you'll see that the two oxygens physically can't go on opposite sides of the plane here. And so you have to go through syn addition. Once you've made the two carbon-oxygen bonds, the water will hydrolyze the metal-oxygen bonds and release the metal, and you end up getting your diol. The same thing happens with osmium tetroxide. Osmium tetroxide has essentially the same structure. Okay, notice the oxygens here are all equivalent, where here they are not. But nonetheless, basically the same structure, same arrow pushing mechanisms. You get the syn addition. Unfortunately, the osmate is actually more stable towards hydrolysis, and that's why you have to add sodium bisulfite to remove the metal from the metal oxygen bonds and replace them with hydrogen. Okay, so that's why you have to have the second step with the osmium. But nonetheless, the mechanism in the first step is the same for both of them, which accounts for the addition being a syn addition of the oxygens to the alkene. Now, it turns out that osmium being highly toxic, you don't want to use a lot of osmium. And it turns out that we can actually create a catalytic reaction where the osmium is only used as a catalyst, so in less than stoichiometric quantities. So you can take the alkene, osmium tetroxide, and the osmium in osmium tetroxide is osmium in the +8 oxidation state, so it's highly oxidized. Once you get the diol, of course, osmium gets reduced from +8 to +6, and this +6 oxidation state of osmium is inactive, and it will not allow it to do additional hydroxylation chemistry. However, we can add another oxidant, which will oxidize osmium 6 back to osmium 8, and then that can undergo chemistry again. And the oxidant that's readily used for this is called NMO, N-methyl morpholine. This ring is called a morpholine ring, N-oxide. So you have a structure like this. And this is a reasonably good oxidant, and it will oxidize osmium 6 plus back to osmium 8, which begins the cycle again. So this is actually our stoichiometric oxidant that's used to regenerate our catalyst that can continue to do this chemistry. Very important that we have a catalytic reaction for osmium because, again, osmium is very toxic, so we don't want to use a lot of it. But also, osmium tetroxide is extremely expensive. So at the time that I wrote these slides, which has been several years ago now, so only the prices have gone up, osmium tetroxide at that time, if you looked in Sigma Aldrich, with the catalog where chemists typically buy this stuff, osmium tetroxide cost over 40 grams per mole. Or excuse me, $40,000 per mole. That's a lot of coin, right? So if you take an alkene, which is cheap, a diol, which is cheap, you can't spend 40 grand per mole on your oxidant. Okay, NMO only costs $190 a mole. So if we use a catalytic amount of osmium tetroxide, we can get away with the high cost because we only need a small amount, and we're using this NMO as our oxidant, which is much cheaper than 40 grand per mole. However, potassium permanganate, if you think about it, it's only about $21 per mole. So on a cost level, you might think, well, why in the world would anybody want to not use the potassium permanganate? And that's true. It's the cheapest. The problem is that it's difficult for us to control this reaction, because if it warms up with the potassium permanganate, you get other products. And so osmium is well behaved. The chemistry is much more well behaved than the potassium permanganate chemistry. But nonetheless, if you're careful, you can do the potassium permanganate chemistry fairly easily. All right, so that's going to finish this quick screencast. I will see you all on Monday. Have a good weekend.